Hello everyone and welcome to the class of Transportation of Natural Gas 1. This class is going to be in two parts, Transportation of Natural Gas 1 and 2. So far we had understood how natural gas is being produced from the reservoir to surface, and at the surface how it is purified to meet the requirement of customer. To send this natural gas which is purified at the surface to customer, we have to adopt certain type of the transportation mechanism. There could be several ways of transporting purified natural gas that is meeting the customer specification which is required in terms of water removal, in terms of contamination removal, in terms of taking out valuable hydrocarbon and selling them separately, as well as same time if the customer needs the natural gas that is having certain amount of energy more than the pure gas, even the traces amount, a significant amount of higher hydrocarbon were also supplied to customer. So, it depends on the regulation, specification of the transportation mode, as well as what could be separated out and at what extent that could be done in the separation facilities. The transportation can be accomplished by several means. This chart shows on the x axis distance the natural gas is being supplied from its source to consumer or from its processing plant to consumer, and the y axis is having gas deliverability, means how much amount of the gas is being transported. The unit is BCM per year, billion cubic meter per year, and the x axis is having the distance in kilometer. So, this relationship shows when we are choosing an option to transport the natural gas, it depends on several factors. One of the factor is how much quantity is being transported and how long it is going to travel. If it is a very high amount that need to travel not very far distance, not very far in the sense, somewhere in this region we can choose either the small pipeline design system or can compress this natural gas and send it in CNG mode, or it could be converting into some other liquid form. All the option can be chosen, and when the distance is going high, we can see depend on the quantity. If the quantity is somewhere in this region, we can still choose pipeline or CNG or the GTL process. But when the amount is too high for a short distance means around 1000 kilometer, it is not like 1 meter or 1 kilometer or just 10 kilometer, it is a 1000 kilometer distance, significant high, but compared to one continent to other continent or from one country to a country where it needs to be transported through a sea line, then the mode will be different. So, if the distance can be covered by the land and the pipeline can be laid out even on the onshore or offshore, and the quantity is significant high, we should choose the pipeline system. And pipeline system is something that is mostly adopted so far for the transportation of natural gas compared to other means. It accounts around 70% natural gas being transported from one place to other place by the pipeline transportation mode. These are the crude data, but approximately pipeline is dominating the transportation mode. When the quantity is high as well as the distance is also too high, like more than 1000, we cannot just lay out the pipeline at certain terrain, certain region because of the geographical or political reason, or by some other possibilities of facing the problem in terms of Bay of Right or other things in the pipeline design. Another mode that is mostly used is LNG, liquefied natural gas. And if we see on the crude data, those are available in the literature and summarizes liquefied natural gas accounts the remaining balance of the transportation around 30%. It does not mean other modes are not being practiced. So, LNG mostly account 30% of the gas that is being transported. This is a proven technology and safe mode, but very energy intensive, require the terminal where it can be deep freeze or the temperature can go down up to minus 160, where this natural gas that is being transported, and the gas which is being transported is mostly methane, and methane needs much lower temperature to go to the liquid phase. And when we are going to minus 160 degree Celsius temperature and liquefying this natural gas, terminals are required for that purpose, and when it is in a special type of the tanks transported from one place to other place in a special type of the tank system, again at the other side terminals are required where it can again be converted into gas phase. CNG also a mode of transportation, and this is stand for compressed natural gas. It is economical compared to LNG because we do not need to go to that much low temperature. However, the compressor is required to compress that thing, but the handling equipment, shipping from one place to other place, the type of the tankers or the shell or vessels are required, allow us to send gas in compressed manner in much economical manner than the LNG. Sea transport can also be accomplished while we are compressing the natural gas and sending it in the CNG mode. A small volume and short distance, when the volume is not too high and when the distance is also not very high, that mode should be adopted, and that is here in this region where the CNG is occupying significant part of this graph. CNG is used in the vehicles now. So, there are significant number of vehicles on the road, those are running on compressed natural gas. If further modification can be done in the mechanism of using the CNG, this may share a larger part. It is having a better future perspective. Other technique could also be possible when we can convert this natural gas or the methane to liquid. That can be done by GTL process. We can do it with Fischer-Tropsch process using a specialized catalyst and temperature pressure condition. This lighter hydrocarbon compound can be converted into heavier compound or other petrochemical compound. Those can be used for other purposes like DME, dimethyl ether, methanol. Those can be generated at the source itself, and then the liquid is being transported through the tanker or by other media. We will be discussing the processes like LNG, CNG, GTL in little bit more detail at the later part of this transportation of natural gas lectures. Let us focus on pipeline that accounts 70% and mostly use mode of transportation for natural gas to transport from one place to a very long distance. When we focus on the transportation by pipeline, we can see a schematic diagram that shows how natural gas can be transported from one place to other place. This figure shows on the left hand side the places from where the natural gas is getting accumulated or gathering station we can call it, and the pipeline are called gathering pipelines. Here I have mentioned gathering system, and when the gathering system is collecting the gases from various sources like the supply from other sources, from gas processing plant where the gas was being treated or processed, and importing part also. They may be having a different part in the pipeline system where they can be included through this trunk line system, the long distance trunk line system, and put it in the main trunk line. So, if we classify this in a broad way, we are having three type of the pipeline system. The gathering system where we are collecting the gases from various sources import, gas processing plant, supply sources, then it is going through the main trunk line and traveling a very long distance. And at the other side, before it goes to consumer, we are having another place, local distribution service load, where these gases are further transported in a small diameter pipeline to consumer, and these lines called the distribution line. Between the gathering system and distribution line, there is a main trunk line where the natural gas is transporting from one place to other place. As already discussed in compressor class, the flow is happening because of the pressure difference and pressure declines because of the friction losses in the pipeline system. That is why several compression stations are required to compress the gas. Two important aspects here: LNG plant, like when natural gas is transported from one place to other place in this system, from the gathering system to distribution line, maybe the demand and supply is not matching, because during the summer time and winter time the demand is different. In the winter time, more natural gas is required to heat the building, to heat the residential areas and for other purposes. The natural gas that is being produced should be stored, that could be stored either in the form of LNG plant, or it can be stored underground in the depleted oil gas reservoir, where we know the geological formation detail. We can store this natural gas there, and whenever the demand is high compared to supply, we can use these underground storage or LNG plant processing facilities to match the demand. Altogether, the pipeline that is here is having different diameter, different specification and similar here, and the trunk line that is spread over a long distance pass through several terrain, like several path it is going to travel. So, when it comes to transportation through pipeline, pipeline design is very much important, because that says depend on the quantity and the distance how to design the specific diameter pipeline. We are not going to discuss other mechanical aspect, we are just on the flow rate, pressure and diameter relationship. So, the pipeline design means appropriate size of the pipeline to meet the throughput. So, we want to send a specified quantity of the natural gas from point 1 to point 2 through a pipeline that is having certain diameter and certain length that we need to travel between point 1 and point 2. How much gas we are going to send through this pipeline depend on pressure difference also. When there was not demand of the natural gas, the calculation involved in this pipeline design were good enough to understand the process. Now, the demand is high, the pipeline system should be used very efficiently even at a higher pressure or the maximum allowable pressure to meet the throughput or the requirement of the natural gas at the other end. That is why the appropriate size of the pipeline to meet the throughput should be considered in the design. Appropriate distance between compression station, as already mentioned, between this long distance between 1 and 2, there might be n number of compression stations are required, that is compressing the natural gas to meet the demand again. So, the appropriate location of the compressor should also be identified. It should be a part of the pipeline design system where the compressor should be installed and at what horsepower working power should be provided to that compressor. So, the specified amount of the natural gas can be transported with the already laid out pipeline system. Pipeline design equation, when we talk about we should do the pipeline design, the design equation depends on the diameter and gas quantity to be transported. Operating pressure and temperature, most of the time it is considered the temperature is not changing and the flow is happening under isothermal condition. The length and the terrain, how long it is going to travel and what type of the path it is going to face, like it is having just a horizontal flow, it is having some inclination, or it should be just a single pipeline, should be a combination of single pipeline, or just a bigger diameter single pipeline, or maybe the looping of the pipeline, that will be discussed in the transportation natural gas 2. So, the complex equation that have been developed for sizing natural gas pipeline in various flow conditions, as already mentioned, depend on how much quantity we are supplying, what type of the terrain it is going to face, the equation may take little bit different form. The typical equations, those are used in the natural gas industry to design the pipeline system or to establish the relationship between the flow rate, pressure drawdown, specification of the pipeline like the diameter and length, as well as fluid properties. That equation can be in a different form. The mostly used forms are Baymouth equation, Panhandle equation and modified Panhandle equation. We will discuss this one by one. An optimum balance is sought between pipe tonnage and pumping horsepower required. How much quantity is being transported through this pipeline and how much energy is required to transport that natural gas, that function or that relationship must be optimized. For economic operation, it is important to preserve full pipeline utilizations. Whatever the mode the pipelines are designed, series, parallel or looped pipeline, the entire diameter of the pipeline, all these things must be effectively utilized for transporting natural gas economically. If we go further and see how to set up the mathematical equations for this pipeline transportation mechanism, the theoretical equation can be set up just by considering the first law of thermodynamics. Several assumptions need to be made. We will make the assumption as we go further and solve the problem or solve the equation that is in the desired form, means how my flow rate is related to pressure drawdown with other important parameter like the fluid properties and diameter and length of the pipeline, as well as the inclination if it is traveling through different terrain. So, under steady state condition, one dimensional flow. So, we are just assuming the flow is happening only in one direction, that is Z, where we are having the pressure difference P 1 minus P 2, the length of this pipeline is L. If it is having certain inclination like this, we can account that with the help of angle theta that this pipeline is making. So, if the pipeline is inclined at a particular angle, we can adjust the gravity forces accordingly. So, for steady state condition, one dimensional flow, considering only the gas phase is flowing, we can modify the terminology saying dry means only the methane gas or mostly the methane gas, sweet means most of the impurities already taken out, and compressible, that is our natural gas is a compressible gas, is flowing through this pipeline of diameter d and length L. For this constant diameter d, we can set up the equation considering it is under the horizontal condition or it is at being certain inclination or the non-horizontal condition the pipeline is laid out. We can see the balance of the forces or the flow driving force, that is allowing the flow happening from P 1 to P 2 will be balanced by three type of the forces. The elevation or potential energy changes that is happening. So, the pressure energy will be equal to the potential energy changes happening in the system. Because of the friction, the pipeline roughness, depend on the roughness of the pipeline, the friction forces will be applied and they will be resisting the flow. So, the friction losses should also be accounted in the balance equation as well as kinetic energy change. We are ignoring any shaft work done on the system. We are just considering a section of a pipe where we are saying the pressure is changing from P 1 to P 2, flow is happening, and that is by applying the first law of thermodynamics, we can set up the conservation equation that says dP by dL is equal to kinetic energy change, frictional losses plus potential energy change in the system. This is one type of the differential equation. If we can integrate this equation, we can get how the pressure drop is a function of flow rate, pipe diameter and fluid properties. If we look more closely on this equation, we can say this equation can be applicable or can be applied for a system where rho, F and EO. Rho is the density of the fluid, the gas which is flowing through the system through this pipeline. F is the friction factor that is offered by the tubing, and U is the velocity with which this gas is flowing through this tube. If they can be defined, we can solve this equation easily considering any analytical solution, and we can get the desired relationship. Depends on the system we are having, we can simplify this equation also. So, for example, when we are having the horizontal flow, this angle should be 0 and we are getting, so this angle should be 0 and we are getting sin theta 0, that is equal to 0, means gravity is not contributing into the system and we can ignore it. Other cases could be there where we are saying the cross sectional area of tube is not changing, the flow is not happening at that high rate where the kinetic energy change is also contributing for this pressure drop, we can ignore this kinetic term also. If it cannot be ignored, either one, either the gravity or the kinetic, we have to include in the equation and more complex equation need to be solved. Let us go step by step. In the first case, we are assuming the gravity is not playing any role as well as kinetic is also not playing the role. The pressure drop is happening because of the frictional losses only, and when we do so, we get very simplified equation that says the pressure drop because of the friction can be related with the viscous shear or the frictional losses, and that is dP by dL is equal to rho some mechanical energy losses of work that is getting converted to heat when the fluid is flowing through this tube. Because of the resistance offered by the tube line, the heat will be released to the environment, and that will be equivalent to the pressure drop happening because of this friction losses. We can convert this into some flow variable. We know how to do it. We did it 2-3 times in the past also, especially when we were dealing with the WPR, Valver performance relationship, where we can establish this is equal to F u square by 2 GCD, and this is responsible for accounting the fluid properties in terms of F. So, thus if we put all of this here, what we are going to get? The relationship that says if the flow through a pipeline is happening in the horizontal tube and no kinetic energy is changing, we got this form of the equation. Just substituting this here, we will get it, and that can also be related by the definition of friction factor, that says friction factor F is equal to tau divided by rho v square by 2. If we put that thing, we are going to get the similar thing. Here the terms are having their usual meaning, like P pressure, the unit may be different, and depend on the unit system is chosen, any numerical coefficient may appear there. If all the units are matching, there will not be any numerical coefficient. We did this several times in the past. So, we can ignore this time. The rho fluid density, now our fluid is not incompressible, the density will change, and we know from our properties of natural gas class how to relate rho with the local condition, that is P and temperature. This is a compressibility should be small z compressibility. 29 gamma g is the molecular weight of that natural gas or the apparent molecular weight of that natural gas. Similarly, when we converting this into the flow properties like the velocity of the fluid, we know u, it is difficult to measure the velocity of u, but we can convert that into some quantity. Those are locally can be evaluated or can be considered. For example, we can convert by knowing the flow rate and cross sectional area u q by a. Again, q is the property of temperature and pressure. we can convert it to Q as the standard condition and we will get this expression. We did this few times before also, should not be having any problem to understand how we got the expression for rho and u. When we put in this equation, we will see now this function is in terms of pressure and temperature. Previously, it was in terms of fluid density and velocity, and they are the function of local condition. We converted them both density and velocity to pressure condition, and when we do so, we are going to get the expression that's appeared like this. After substituting the value, we can also get this expression. So, this is rho value. We got the equation how the pressure drop is happening when the fluid is flowing or the gas is flowing through a pipeline of diameter d at a particular length. In this pipeline, we can estimate the pressure at the end or at any location after solving this differential equation. But again, the problem is not solved, because we see here when we converted this, we are having F and U. This equation, which is a balance equation or energy balance equation under certain conditions, says how the pressure drop is related to fluid properties, and it serves the basic equation for the development of any pipeline equation under certain assumptions. Those assumptions may create some problem or some deviation from the result obtained by this equation. For example, gravity, kinetic energy were not considered, steady state condition may not be a case when flow is happening, and shaft work is not considered. There might be some additional work done on the natural gas from the outside, but under certain assumption those we had discussed, this mathematical equation is good enough to represent the flow through horizontal pipeline under steady state condition through a pipeline of constant diameter. The difference in this equation originated from the method used in handling the compressibility factor and friction factor. So, in this equation we will see the compressibility is appearing and F is appearing, and both are having dependency on other parameters. Similarly, we will see the U also depend, because by the definition U is also a function of temperature and pressure. Now, when we integrate this equation, considering all these terms are constant, although those are not constant, we will see we will get this kind of the expression where it says inside the integral we are having the pressure, temperature and compressibility. Temperature may be assumed constant or may be taken average. Similarly, the pressure, either we are evaluating it locally or we are taking it as a constant or the average by any mean. Once we know the temperature and pressure as well as gamma g of the system, we can calculate the compressibility, as we know from our properties of natural gas class how to calculate the compressibility. We may discuss one example to understand the procedure of performing the calculation for pipeline design. Integrating this equation may result in a simple expression, but before we go further, we see the friction factor U is a function of Reynolds number and of the relative roughness of the pipe. We cannot take it out of the derivative term, because it is a function of Reynolds number. Reynolds number is a function of flow rate. Flow rate is a function of temperature and pressure. Similarly, for U also. So, let us see what we can do for each term when we go further. For velocity, we can simply, this can be converted in terms of temperature and pressure, and we can put it inside the integral sign. For the F friction factor, it depends on which form we are going to calculate the friction factor value. So, if we look in the literature, we see the friction factor versus Reynolds number relationship, that is also called the Moody's chart relationship, that account for the changes happening in the value of friction factor when a gas or any fluid is passing through a tube of some roughness and some diameter. So, this relationship is on log scale. On the y axis is the friction factor, on the x axis it is Reynolds number, and there are several lines, those represent for different relative roughness of the pipe. If we classify this chart, we can see there are 4 regions. One is laminar flow, where the flow is not dependent on the roughness of the pipe, it is just a viscous flow or not very high flow rate is present in the system. In most of the cases in pipeline design, we are in the turbulent region. Before we hit the turbulent region, there is a transient region where the distribution in the value of friction factor is not that high with respect to epsilon divided by d. Then the third region is complete turbulent region, and fourth one is smooth pipe region, where it is not depending much on the Reynolds number, just it depends on the roughness of the pipe. It is important to understand this chart is in terms of Moody's chart, not in the fanning friction factor form. So, the value of F we are getting from here is a Moody's friction factor F m, that is I mentioned here. F m is a function of Reynolds number and roughness. Depend on which region we are, it is depending on Reynolds number or not, it is depending on the relative roughness of the pipe or not, and what value should be chosen depends on under what condition the flow is happening through the pipeline. For example, in the laminar region, we can see here from this chart, this is the region where the friction factor is just a function of Reynolds number, and it is having the reciprocal relationship. So, the Moody's friction factor is just can be calculated by 64 divided by the Reynolds number. We do not need to worry about the roughness of the pipe. And if it is a fanning friction factor chart, we will see the relationship between F m is equal to 4 times fanning friction factor. Accordingly, the adjustment need to be done. In case of fanning friction factor, we will get F f is equal to 16th by N R e. So, we are seeing here the 16th by N R e, this point we will see this chart is with respect to the fanning friction factor, otherwise it is Moody friction factor. The relationship in the laminar region can be established by well known phenomena of Hagen-Poiseuille flow in the pipeline. Due to the characteristic of complex nature of the curve, several equations have been designed for this region, all 3 regions, transient region, turbulent region and smooth pipe region, and accordingly we can choose which region the flow is happening in the pipeline. Not only the region the flow is happening in the pipeline, but we can see how it is changing with respect to Reynolds number and epsilon d. Several expressions have been reported in the literature in the form of correlation. We can choose based on the limit, range or condition specified for each expression, that we can see in the next slide. We already discussed similar kind of the things when we were developing the relationship for WPR. In WPR, we were having the vertical flow of the gas from PWF to PHF. We discussed the phenomena with some inclination, and later on we solved the problem for vertical flow system. Let us come back to our problem, where we said the friction factor F is a function of Reynolds number and of relative roughness of pipe. Yes, we know by the definition of F or from the Moody's chart, it depends on how to estimate relative roughness ED. It is defined as relative roughness of the pipe to the pipe internal diameter epsilon by d. It is the values should be provided by the vendor who designed the pipe or who is supplying the pipeline. In cases it is not available, we can calculate by performing certain experiment and see comparing the pressure drop is happening in a particular pipeline compared to the very smooth pipeline, we can estimate this value. Or in other case, when we do not have the value, we are dependent on somebody, we can choose very acceptable value of epsilon, that is 0.0006 inches, and divided by the diameter, we can calculate the relative roughness. Now, we know the relative roughness, now we need to know the Reynolds number to read the Moody's chart. We know by the definition of Reynolds number, Reynolds number is equal to rho v d by mu. By adjusting the parameter as we did in previous classes, we can establish the relationship Reynolds number is equal to 20 q gamma z mu d. So, it depends on q and q depends on temperature and pressure. That is why when we are going to read the Moody's chart, we should know the flow rate, and if we are going to calculate the flow rate, we have to perform the iteration. So, depend on the flow regime, we are in the laminar region, turbulent region, transient region or later turbulent region, we can establish the either we can read the chart and can get the value of f. For the single phase and multi phase, the system will be different. We have to be little bit careful when we are talking about the multi phase system. For the laminar flow, now we know Moody's friction factor is 64 by NRE. In case of turbulent single phase flow system, for f value there are several expression, only few of them are included in this. Several we discussed already in the class of WPR. So, for a smooth wall pipe, Drew, Coe and McAdams in 1930, they had designed or established the correlation that says when you are in the Reynolds number of 10 to the power 3 to 10 to the power 6, you can use this expression, and that says it does not depend on epsilon d. You can just establish the value of f knowing the Reynolds number value, and this is for a smooth pipe. When it is a rough pipe, Nikodse had developed a relationship, and that relationship is widely used for the pipeline design because it did not depend on the Reynolds number. And you see here, this is just E d, that is epsilon d. So, to calculate the value of f, we need to know only the roughness of the pipe, and if roughness of the pipe is known, we can get the value of f. This is valid for large value of the Reynolds number where the effect of relative roughness is dominant. It is not the value of the Reynolds number, but the effective roughness that is more contributing towards the deviation in the f value depend on the condition. So, for epsilon d value, we can use this expression. Goa and Galambor showed that this expression given by the Nikodse for friction factor is valid not only for the gas flow, but gas flow with some solid and liquid mist. The same expression can be used. Further, the expression accounting the range of the flow where both epsilon by d as well as Reynolds number are going to dominate the phenomena is developed by Colebrook in 1938, and the relationship says we can also include Reynolds number in the Nikodse expression, which accounts for the Reynolds number effect on the calculation of f. This expression can be put back to Nikodse if we assume Reynolds number effect is not significant. This equation will be similar to what Nikodse has proposed. Now, in this equation, the problem is on the left hand side we are having the friction factor and right hand side we are having the friction factor. To solve this kind of the equation, we need to perform the iteration procedure either by the Gold-Seek or Newton-Raphson method or other optimization method. We can perform the trial and error procedure or the iteration procedure to establish this relationship. And to avoid this difficulty, Jain in 1976 modified this equation and proposed a equation that says you can use this equation which is having E d and Reynolds number both, but does not need iteration. And this equation proposed by Jain is recommended for all calculation requiring friction factor determination to a system where the turbulent flow is happening. So, let us come back to our theoretical equation where we say this equation which was accounting for change in potential energy, change in friction losses and kinetic energy change, for those are contributing to pressure drop, with the help of non-parameter like how to convert rho and velocity into temperature and pressure condition, we could establish this relationship. And that relationship says, now if you know f, how to count it, can you take it constant or not? Similarly, for U2, you can solve this expression. We know u2 cannot be taken out, it has to go inside of this integral sign. Using this relationship, when we integrate this, we are going to get this expression. To integrate this equation, we have to make certain assumption for the temperature. We can assume the isothermal process is happening, there is no temperature changes happening, or temperature change is happening is represented by the average temperature T bar. Similarly, the compressibility factor Z is measured at average temperature and average pressure condition. So, average temperature can be calculated like this, like if any temperature change is happening, we can average out, and for pressure also we can go by the arithmetic average P1 plus P2 by 2. At this temperature and at this pressure, we can calculate the compressibility factor, and that can be taken out of the integral sign, assuming it is constant in the process. And when we integrate this, we will see after doing the separation of pressure term on the left hand side and others on the right hand side, we got this expression. If we can rearrange the things, we are going to get in terms of Q, where inside the root we are having P1 square minus P2 square d to the power 5. And d to the power 5 came because in U square we are having this Q by A. So, when we square it, it became Q by A square, and from here it became d to the power 4. 1 d was already there, we could get d to the power 5 here. After adjustment, seeing this is TB, PB at a particular base temperature and pressure, we can relate Q with pressure drawdown or pressure difference in the square form. D to the power 5 means the diameter of the pipeline, gamma g specific gravity or the property of the natural gas, average temperature, average compressibility, F is still there, the F value will be put up there, and the L, the length of the tubing. So, all are having the usual meaning here, depend on the unit system specified for each. We will get this C, the numerical coefficient here, that may get different numerical number. But see here again, this equation which we got after doing the integral, after making certain assumption, we see the Q on the left hand side is again depend on F, that is friction factor, and if F is calculated by Reynolds number, iterations are required to come out the accurate solution of this equation. The specified substitution use may be diameter dependent, that we already know. If we are having the F, that is just depending on diameter of the tube, either it is small di or capital D, or it is depends on the Reynolds number only. Panhandle equation are derived based on certain assumption. So, in the Bemouth equation, it is just a function of the diameter, and in Panhandle equation, it is a function of just Reynolds number. We will see this in the coming slide. So, now the equation that has been developed here is only for horizontal flow. We had considered theta is equal to 0, and we had neglected this term as well as the kinetic term, assuming constant diameter tube. Now, we can derive the same equation considering the theta is not 0, it is having particular inclination, the pipeline is having inclination from the surface. We can establish the relationship for non-horizontal flow condition also. We will do this later on. So, let us go for the horizontal flow. What we got when we convert the unit, as I mentioned in the last slide, the numerical coefficient C that is appearing in the last will get changed. Now, this Q also got changed here, it became QH. It means the flow rate is measured per hour, standard cubic feet per hour, and the numerical coefficient appear here. Remaining things are same. It has been taken out outside, and this term is called transmission factor. So, 1 by F and its root is called transmission factor. The Moody's friction factor may be a function of flow rate and pipe roughness that we discussed. Depends on the functionality of the F, this may take different form. For fully turbulent region, F may be defined like this, where it is not a function of the Reynolds number, just the relative roughness ED, or in other term epsilon by D. We can say using this, it is not depending on the Reynolds number. If not complete turbulent region is there, F depends on Reynolds number, and we have to calculate the Reynolds number, put it in the equation of F which uses the Reynolds number, and iteration need to be performed to calculate the QH value. So, now depend on the F functionality chosen, the mathematical equation, that is the solution of just a simple balance equation, may take different form. So, for example, Baymouth equation that is widely used for the horizontal flow, eliminate the trial and error procedure, just assuming F is a function of diameter only, and if we express F in this form 0.032 divided by d to the power 1 by 3, we will get QH. Again, QH means standard cubic feet per hour, the flow rate with respect to some base temperature and pressure will take this form. Here, because of d, the d to the power 5 got converted d to the power 16 by 3, and other things are almost same. The Baymouth equation commonly used in the natural gas industries to establish the relationship between Q, pressure, temperature, diameter of the pipe and other properties. But this equation is under certain assumption. What we assumed, no mechanical work is done, steady flow is happening, isothermal condition is assumed. So, T either it is isothermal constant temperature or T bar is chosen to represent the flow. Constant compressibility factor Z bar, it is constant. So, it is calculated either at a average pressure, that average pressure could be just arithmetic average P 1 by P 1 plus P 2 by 2, or maybe the arithmetic average of compressibility itself. So, compressibility is calculated at pressure P 1 and then pressure P 2, we got Z 1 and Z 2, take the arithmetic average of both, we are going to get the average value of compressibility. Or it might be defined in other form, where how the compressibility is changing with respect to pressure in this pressure range P 1 to P 2, integrating that area under that curve in the form of P 1 to P 2 Z d P, we are integrating from P 1 to P 2 divided by this range P 1 to P 2, we can get the average value of the compressibility. The pressure may be chosen either arithmetic average or maybe in other more complex form, which provide more accurate value of the average representation of the pressure. That depends on how pressure is changing with respect to P 1 and P 2, can it be taken as the average. Similarly, the compressibility factor Z, how it is changing linearly with respect to pressure, maybe just average is good enough, or if it is not changing linearly with respect to pressure, we may use this area under the curve approach to calculate a compressibility value at average condition, or it is the average value of the compressibility factor. We also assume the flow is horizontal, theta is 0 and no kinetic energy change is happening in the system. If any of the assumption mentioned here is not applicable, we have to modify the equation, because the results obtained by setting the mathematical equation under this assumption will deviate from the real results, and that can be done by including term into the equation, like we did in WPR, where the flow was happening at an inclination angle and we assume gravity plays important role. In fact, in a vertical pipeline system, gravity plays major role to balance the pressure drawdown around 75%, and that is where we could establish the relationship. Similar we can do for transportation of natural gas pipeline also. Another method, that is Panhandle A equation. Panhandle had given two equation, Panhandle and modified Panhandle equation. We can say Panhandle A equation and Panhandle B equation. In Panhandle A equation, for the horizontal flow, it is proposed the F is not just a function of diameter, it is a function of Reynolds number only. In other terms, Reynolds numbers include the diameter, so it is including the diameter, but not including the roughness of the pipe. And if it is assumed in this manner, put in the equation that we had, we are going to get the resultant pipeline flow equation in this form. This is little bit complex because Reynolds number will impose all these parameter on the system to be included, and we will get this expression where all the terms are like P1, P2 are there, average temperature, average compressibility factor, L are there, gamma G power got changed and d to the power also got changed. Here the numerical coefficient again depend on the unit system, and here it is considered as Q is the gas flow rate in CFD, cubic feet per day, measured at base temperature and base pressure. Other terms are same as we already consider for the Behemoth equation. In Panhandle B equation, this is a modified form of the Panhandle A equation, where it is assumed the modification has been done in terms of, so the power of the Reynolds number and the numerator coefficient both are little bit modified to propose more accurate equation to account the relationship between the Q and the other parameter, and the equation will take this form. We are not going to put these values and reaching this equation, it is an exercise you can do, and the important is you will get this expression of Q in different form depend on how f is chosen and how f is related to one particular parameter like epsilon d and Reynolds number, or it is just a diameter, or it is just a Reynolds number. And with respect to Reynolds number also, it is in X form or in the Y form, as it is done in Panhandle A and Panhandle B model. Let us understand what is this transmission factor under root 1 by f that appear in the mathematical equation that we established for the flow through pipeline, and that form depends on the system has been chosen. So, for the smooth pipeline system, we can say it is just a function of Reynolds number. When Behemoth equation consider only the diameter, Panhandle consider Reynolds number with different numerical coefficient, then Panhandle B equation. For the rough pipe, we can just ignore Reynolds number and can just include the ED, relative roughness of the pipe, to have the transmission factor, and ultimately that transmission factor will give us the value of F friction factor. Another thing that did not count in establishing the relationship is pipeline efficiency. All pipeline flow equations developed so far are based on the consideration that only gas is flowing through the pipeline. This is a single phase system, but in actual practice water, condensate and sometimes a small amount of the oil are also present with the gas get accumulated in a pipeline and cover some part of the pipeline, means they reduce the effective diameter through which the gas can flow. They create some more problems also, we will discuss later on, but the presence of these liquid in the pipelines reduce the efficiency of the pipeline to transport the amount of the gas from one place to other place. That is important with respect to the transportation. There are often scale formation or junk left in the line, and to account all these things there should be a term that should be multiplied with the expression obtained, that says the correction in the flow rate that is actually transported than the theoretical value. So, the equations based on certain assumption considering ideal cases are giving us the flow rate that theoretically can be transported. For calculating the actual value, it can be multiplied by the pipeline efficiency, that comes in the range of 0.85 to 0.95 compared to clean line. And the table shows for a type of line like it is a dry gas, you can use 0.92. If casing head gas where the gas is having all sort of the impurities as well as higher carbon number hydrocarbons, then the efficiency will reduce 0.77 only, and the gas and condensate are present, then the efficiency will further go down 0.6 and depend on the liquid content. So, this also says how much liquid is content in the system in gallon per mmCF. The efficiency factor should be multiplied with the theoretical equation to get the actual value of the gas that can be transported through the pipeline which has been designed to transport the gas. So, in summary, we can see in a horizontal flow system, we are having the Bemeth equation, Panhandle equation, Panhandle B equation, and the only difference is how the F is chosen, we are going to get the different things. Here the Q is mentioned in QH, that is why the different numerical coefficient 18.062 is appearing here. If it also transferred to per day, we will see the same value or near about the same value, that is summarizes in this table also. So, if all these three equations can be represented in an empirical formula here, this is a more general way of expressing the flow through pipeline or flow through horizontal pipeline. We can say the A1, A2, A3, A4, A5 can be written for each equation Bemeth, Panhandle and Panhandle B equation we can summarize from this table. Like for example, Bemeth, here it is written 433.5, as I said this is in hours. If we convert this into days, we will get the similar thing 433.5, and others like here we got 16 by 3. If we divide this, we are going to get the same value with respect to the diameter A5 2.667. So, this represent the general form where the coefficient value A1, A2, A3, A4, A5 depends on which model equation is chosen and what are the unit are associated with each parameters involved in this expression. These expressions are certain under certain assumptions: no mechanical work under steady state flow condition, isothermal flow, constant value of the compressibility factors, only the flow happening in one direction, that is also with the horizontal flow only, and no kinetic energy change is happening in the system. If kinetic energy is changing in the system, we are having this term U du, and if this is there, we know how to convert this U. Similar, this U will also get converted, and we have to include this in the expression, and additional term we will be getting in our system, that will be like minus 4 Q ZT pi d square PSC TSC, standard temperature pressure condition. So, this will also become QSC to the power 2 dP by P to the power 3. And when we are including this term in our energy balance equation, ultimately we will get in the form of P1 square minus P2 square. Additional term you will get because of the kinetic energy is ln P1 by P2 along with other terms here. So, for the horizontal flow, there are some other equations also available in the literature, like this Klein-Dienst equation, that account how the pressure changes happening in the system is going to affect the behavior of the natural gas, means the deviation of natural gas from the ideal gas can be represented by this equation. So, the compressibility factor is inside the integral sign, and it is integrated from 0 to first reduced pressure at condition 1 and 0 to reduced pressure at condition 2. Here we can get the expression, and this expression may give us more accurate result in terms of the deviation of natural gas is more compared to ideal gas. So, the ZB gas deviation factor is calculated at TB, PB normally accepted as 1.0. Based on the pseudo critical pressure, the value of integral function have been calculated for various gas. In one of the appendix, there are several data have been compiled for this method. The expressions are usual here. Q is mCF per day, pressure in PSIA, D is in inch, length is in feet, P are pseudo reduced pressure which is having no unit, and T bar is in degree ranking, and gamma z is gas gravity. When we talk about Behemoth equation for non-horizontal flow, we see the gas transmission line for the non-horizontal flow are often appears when we talk about long distance natural gas flow system. At several places the natural gas pipeline is not horizontal, but it is having certain inclination from the surface, and depend on the terrain it is going to cross, this might be appearing very frequently. For that case, we have to account how the gravity term is going to affect the relationship, because in this kind of the system the gravity will also be very important. Considering that thing, we have to establish the relationship again, and that says this term cannot be ignored. However, kinetic energy can still be ignored if the constant diameter pipe is used. So, considering gas flow from one point to another point in a non-horizontal pipe, the first law of thermodynamics will take this form. Here this is pressure. So, here this is specific volume, that is 1 by rho. Del z is just the inclination. We can say del z is equal to, it is similar to the elevation vertical distance from this to this. This is del z, and f is having usual meaning, u is having usual meaning, d and del L. Again this can be described, the pressure drop is happening in this del z length can be gamma z by 144. 144 is because of the conversion factor, like this. Gamma z is okay. We know how to convert this density of the gas in the pressure and temperature term. Again the velocity, we already did this in our WPR class. In WPR class, where we understand if we are having the gravity term, friction term and pressure term altogether, using the separation of variable after making certain assumption, we can convert this in the form of P dP upon some constant plus some B constant, and integrate this from P1 to P2 for length L, and where we had taken this A plus BP is equal to x, and we could integrate this by having the variable of separation, and finally we got the expression in the form of e to the power some value here. If we do the same thing, we will get the same expression. So, instead of repeating the expression, what I can show you, the Behemoth equation for non-horizontal flow will be distinguished by this term compared to what we had for the horizontal flow, this e to the power s, while s is a function of gamma z, this elevation del z, average temperature, average compressibility. The del z is equal to outlet elevation minus the inlet elevation. Del z is positive when outlet is higher than inlet. So, this sign will depend on the elevation, it is upward or it is downward, the flow is happening. A general and more rigorous form of Behemoth equation with compensation for elevation can be represented like this, where the difference from this equation to this equation is this L E. L E is the effective length of the pipeline. That means, if the effective length of the pipeline is included here, we can get more general and rigorous form of the flow. So, remember this expression is written for Behemoth equation, similar can be written for the panhandle A and panhandle B. The effective length is e to the power s minus 1 divided by s multiplied by the actual length. And when there is a situation when multiple different elevations are appearing in the pathway, we can adjust again with the effective length L E, considering these multiple inclination either upward or downward, considering this formula e to the power s 1 minus 1 divided by s 1 multiplied by the length L 1, and then in the next term it will be e to the power s 1 plus s 2, e to the power s 2 minus 1 divided by s 2 L 2, and if we write the end term, it will be e to the power s 1 plus s 2 plus s n, e to the power s n minus 1 divided by s n. So, summation of each individual segment or each individual inclined segment, we can get the effective length value here. Here S is having the same value, only the thing is this del z I, for each segment the del z I value will be different. So, we can establish now relationship for horizontal as well as for non-horizontal flow condition. Now, in the next class we will understand using the Baymouth equation how to establish the relationship between Q and other parameter. We may solve one problem on that, and how to lay out the pipeline design considering the concept of series pipeline, like here where the pipeline diameter changed, it is in the series, and when we are establishing the parallel. So, this is parallel, this is series combination, and this is looped where some part of the pipeline is in series, some part in the parallel mode. We will consider all this with Baymouth equation, but equally we can do with other form of the equation, because the equation differ in terms of how friction factor is included in the balance equation. So, with this I would like to end my today's lecture. In tomorrow's lecture, along with the pipeline, we will also discuss about other mode of natural gas transportation. Thank you very much.